last time was losses. I just want to go over that a little bit and then talk about thermal design. Again, it's not in your textbook, except that there's a little bit about it in chapter 10, so I would like to make sure you're comfortable with this. So again, generally, any switch will have current when the device is on. When the device is off, current will go down to theoretically zero, but there is some leakage current, right? And then when the device is on, the voltage is theoretically zero, but it's not, because there's a voltage drop across the MOSFET and the BJT. One is due to the RDS on of the MOSFET, and the other is due to the junction voltage. So even when it's on, when it's off, it's blocking the full voltage, right? So typical waveforms, we said, will look like this, right? So this is my voltage, and typically, if this is V, and then the current will typically coincide, the rise of the current will coincide with the fall in the voltage, but we said to simplify our calculations, we will sort of shift the rise in the current a little bit, or the rise in the voltage a little bit, so that they don't coincide. So that we don't have a parabolic, right? So we will have something more of this is rising, this is constant, this is falling, this is constant, right? So basically, I'm taking, if I'm looking at power loss, instantaneous power loss, then my P of t, which is V times I, will look something like this. If when the device, this is no current, right? Means the device is off. But there's actually some leakage current, and then there's some voltage across the device, right? So there will be some power loss, right? And then how about during this time here? Right here, it's a ramp up, and then right after it's on, the voltage starts dropping. So I mean, these two coincide. This peak and this peak coincide to some extent. So we'll have sort of a triangle here, and then there's this is the device on time. So device on meaning current is flowing, and there is a voltage drop across the device that is equal to either the current square times the RDS on, or the voltage across the junction of the BJT type device. So here we also have conduction loss, right? And then we have that current falls down. So this is turn on, and this is turn off, right? So this is your turn on, and this is your turn off of the device. Okay, so after it's turned on, there's conduction current, then it's off. Okay, I will ignore the leakage current here. And this would be my, this is happening when? This is happening every period, right? So the device can turn, it's off, then I turn it on, then there's conduction, and I turn it off again, and then maybe I repeat this. This is your switching period T. I will keep repeating this every now and then, right? So this is your instantaneous power, right? I would like to calculate my average power, because average power to the device is what raises the temperature of the device. So this average power would be due to the conduction loss, average conduction loss, and then it will also be due to the average turn on and turn off power losses, right? So, and we said that the peak here is equal to, this is my rise time, and this is my fall time. Rise time and fall time of my switch. This is in the data sheet from the switch. And then the peak here is basically this voltage and this current, right? Do we agree? And in all the power converters that we looked at, the current that's flowing through the device is going to go where after that? Like, let's look at the buck converter. This is my current to this device. It's going to go split up between it's going to go through the inductor. after that, right? So the switch current is typically equal to the peak value of switch current will typically be equal. This is the peak value of switch current, right? This is my peak value of switch current, assuming it's flat. Forget about the ripple current for now. Assuming the inductor current ripple is very small. So it's the peak value of this switch current is equal to the peak value of the inductor current, right? So this is typically going to be what? Equal to your inductor current. This peak value here will be the value of current flowing through the inductor as well, right? It's the peak value of inductor current, right? This peak value of inductor current is what I will take. This peak here is basically IL peak multiplied by what voltage? The voltage across the switch combination, right? For the buck converter, the switch combination has V input across it, right? For the boost converter, the switch combination has V output across it, right? The boost converter right? This switch combination here has V output across it, right? And then for the buck boost, it's V input minus V output, right? So one is V input, one is V output, one is V input minus V output. That was the voltage of the device, right? So the peak voltage that the device is seeing is this, right? So this is some V peak across the device, and this is I peak through the device. I peak through the device, which is equal to the inductor current, actually, inductor current peak, right? So this peak is Vp times I peak. So we said that the turn on energy loss was equal to half base times height. And the turn on, so this was turn on energy loss. Turn off energy loss was equal to half base times height as well. V peak times I peak. And this V peak times I peak depends on the topology. Okay? The V depends. The I does not really depend. I will always be the peak value of inductor current. But the V here will depend on which converter you're talking about. Okay? Make sure you note that. And then we said that the P total, the total power loss in the device, is equal to the switching turn-on loss plus the switching turn-off loss plus the conduction loss. This is the total P loss. This is power loss in the device. I'm trying to calculate the average power loss in the device, right? So since I'm trying to calculate the average power loss in the device, I need to look at one period, right? And then I'm taking the integration or the area under this curve for one period and then divide it by the period. So this is the integration or the area under this curve happens to be this half base times height. If I take this and I want to find the average value of this area, right? What is it? It's basically this area here, half base times height, divided by my switching period, right? So it just happens to be, this happens to be energy, right? The area here happens to be energy. But what I would like to do is figure out what's my average power loss in the device. It's the average turn-on power loss, average turn-off power loss, and average conduction loss, right? That's what it is basically. So it's half base times height, half base times height. I will take this eon and divide it by t, right? Which eon divided by t is equal to what? Divided by t is like multiplying by, it's like taking this, since this is energy, then I have power. So if I take energy and divide it by a period, this is my energy during one period. If I take energy and divide it by period, it's power basically. And this is like writing this as, I can rewrite this as half base times height multiplied by switching frequency, right? That's P loss. That's the turn-on component. The turn-off component is half T fall times height times switching frequency, okay? Plus conduction is what? Base times height is basically the duty cycle, right? This is a pulse, right? Conduction loss is like a pulse, right? This pulse has a peak value of what? It has a no. It has a it's some voltage when the device is on, because when the voltage when the device is on will depend on what? If it's a MOSFET, it's the I squared times RDS on. If it's a BJT, it's the forward voltage drop. So let's say it's a BJT, it's the forward voltage drop of the device multiplied, so it's the V on of the device. V on of the device can be I squared R, or it can be the forward voltage or the junction voltage across the device, right? It's the junction voltage across the device is one, the other one is I squared R. And this has an average value, right? So this is, the height is V on, and the width is D times T, right? So it's D times T multiplied by D times, what's the peak value is V on times what? Times the current flowing through it, which is IP, right? So it's the peak current flowing through the device. It's the current flowing through the device multiplied by the voltage here. That's the peak value of this. That's this distance here. This distance here is V on of the device. And then multiplied by IP of the device, which is this current, the value of this current here, right? This is a pulse that lasts for a period of dt. So what's the average value of this pulse? It's dt times V on times, sorry, let me write this here. It's dt times V on times IP. That's the average value of this pulse.
You just divide by the period again?
What?
Don't you just divide by the
That's average value, that's energy. So turn on, that's conduction loss energy. And if you divide it by T after that, because the area is what? If I multiply dt, which is this is the on time, dt, right? So this is the base times the height of the rectangle, right? Base times the height of the rectangle, that will give me this area. This area is energy. If I want power, I divide it by t. If I divide it by t, the two t's goes away. The two t's go away, and I end up with d times V on times IP. So it's d times V on times IP, which is basically the average value of this power loss peak, this power pulse, basically. Okay? We're okay with this? So what do we do with this after that?
efficiency.
So we can calculate efficiency. Of course, we can calculate efficiency, and the efficiency is what? Efficiency is equal to power output over power input, or power output over power output plus P loss. Right? So assuming we only consider the loss from the switches, this is how we can calculate that. And then what do we do? What's another important thing is we want to design. You want to actually select your heatsink. To select a proper heatsink, what is this heatsink doing? It's helping you reject the heat. Reject the heat coming from where? From your power loss, right? So this will affect the device temperature. So this is a package here. This device here has a silicon inside. This silicon junction is going to be a certain value. This junction temperature, if you go to the datasheet, we will see that this junction temperature will be given the maximum junction temperature, TJ max, not the store, TJ max, the maximum junction temperature, will be given in the datasheet. 150C, 175C, whatever it is for the device, right? So, and typically for applications, for commercial applications, I think it's when you design your power converter, when you develop something like a commercial laptop, right? You don't design this so that your junction temperature in a device is 150C. Typically, or you don't do that, because equipment that is rated for commercial application is typically going to be allowing maximum temperatures to be up to 85 degrees Celsius only. Military grade or vehicle automotive grade electronics will go up to 125 for automotive, and then 150 for military, right? So they have different maximum junction temperatures for components. So you may be buying the same processor from TI. So TI has the same processor, but packaged in such a way to reject more heat easily. Because again, this is it's the packaging. The silicon is connected, it's put inside this package. This package, is it metal, big surface area, small surface area? Is it plastic? Is it thermally insulated, thermally conducting or not? Right? So depending on the package, you will be able to reject heat better. I don't know if it's clear, that's clear or not yet. But the silicon can be exactly the same. Actually, the silicon is the same. The package is different. And you would design your power converter to make sure that you maintain the maximum junction temperature based on your device datasheet. This will be equal to your ambient temperature plus your power loss times the thermal resistance. And this is a number from the datasheet. And this is a number from the datasheet as well. This is thermal resistance. This is called thermal resistance. Huh? This is the maximum allowed temperature for the device. And this can be in the datasheet. The TJ Max will be in the datasheet. But I can be designing something and tell you I don't want the junction temperature to be greater than 100 C, because I want when somebody touches that piece of, because maybe that piece of equipment somebody will hold in his hands. I don't want the maximum junction temperature to be greater than 50 degrees C or 25, whatever, right? Or you may be having it may be inside a box, and that box maybe have some insulator, and then somebody's going to hold that in his hand, right? So you will have a maximum limit on the temperature of the junction, because that will affect the power loss and affect the temperature rise of the equipment around it, yeah, right? So you're typically going to be given, okay, design a power converter so that your junction temperature does not increase, go over 100 C, for example, right? And this power converter is operating with an ambient temperature. This is ambient. Ambient meaning where the converter is operating. You're operating in a room of 25 degrees C. So, and you are selecting a device now, right? So you have two things now to play with: power loss and thermal resistance. Thermal resistance, you may have selected the device with a maximum. Remember, how do we select devices for a MOSFET? How are we selecting MOSFETs? Average current and peak voltage, right? So you went to the IR website or the TI, whatever vendor website, and you selected a MOSFET for a certain maximum voltage and certain average current. After IR has a website, a filter. You will go to that website and you put these two numbers, and they will give you 20 devices that can satisfy that requirement. How do you select after that? You will select after that based on, power loss and R thermal, for example. That's one of the things that you will select on, because you will select. Let's say your goal is to design something that is very small. Are you going to be able to put a heatsink? Probably not. But if your goal is to design something that is very efficient, can you? And it's not, does not necessarily need to be small. Then in that case, you can put a heatsink, for example, right? So if you cannot put a heatsink, that's the easy case. If you cannot put a heatsink, then what would be your criteria for selecting the device? You will go for the device with the smallest thermal resistance. Thermal resistance meaning the resistance to rejecting the heat outside the device. So if it's small, and this is typically in degrees C per watt, the units are degrees C per watt. So if it's a small number, then the resistance to rejecting heat is very small, meaning you should be able to reject heat easily, right? So let's say this is 1 degree C per watt of loss. It's degree C per watt of loss. And what heat are you rejecting? You're rejecting the heat generated from your power loss, right? So then you would go back and calculate your power loss, right? So you go back to calculate your power loss. And then then you go back to the equation for the power loss that we talked about. Half base times height VP times IP times switching frequency plus half time fall times height VP times IP times switching frequency plus DT plus D times V times V on times average current IP, or the maximum current, sorry, the maximum inductor current. So you go back to this equation, right? So what can you play with? You've selected your device, so you probably have TR fixed and TF fixed, and your circuit has certain input voltage and output voltage, so you probably have VP and IP fixed, but you can play with frequency, right? So then you maybe go back and change switching frequency. Maybe decrease switching frequency to limit power loss. If you decrease switching frequency, then what are you going to do to your inductor? You're going to go back and calculate your inductor and capacitor size. You may be increasing those, right? So there will be a limit where you're increasing the capacitor inductor too much, and your objective was to make a small power converter, right? So you would iterate. Select an L and a C, given a switching frequency. Then go and calculate your power loss. Maybe in that case, for the given L and for the given C, you had chosen a very high switching frequency, and which would have caused your temperature, your junction temperature, to go up. Then you would iterate, reiterate, and design the converter again. Does it make sense? Does the process make sense? Excuse me? You will have a criteria, right? You will have a criteria. Maybe some range of capacitors. Like if you go to the data sheet on the website for the capacitors, the capacitor in a certain package can come. They can provide many capacitance values. So maybe if you go to another capacitance value outside that range, the size will change, right? So you will reiterate. Again, you select your switches. Select some base switches, and then you select some inductor and capacitor, and then you calculate your efficiency, and then you calculate your power loss. Are you okay? What are you trying to optimize? You may be trying to optimize power loss because you want to maximize efficiency. You may be trying to optimize size. If size is your objective, then it's okay for the power loss to be a little high. The device temperature may go much higher than normal cases, right? So it's an optimization criteria, right? So, but you have the equations now to select L's and C's depending on switching frequency, because the way we select L's and C's is by looking at the areas under the curve, right? Delta Q and my delta lambdas, right? This is my delta lambda is to select L. My delta Q is to select C. This waveform here, the width, or the amount of area here, depends on switching frequency, right? If the switching frequency is high, then this waveform here will become narrower, right? For the same duty cycle. Like duty cycle will not change, because duty cycle depends on input and output voltage, and that's it. So you select duty cycle, and then you want to select L and C. You select L and C, but you will have to select some switching frequency to start with. So you start with one and draw the corresponding waveform, select the L and C based on your delta Q and delta lambdas. Right. Then you will go and calculate your power loss, because you have to calculate power loss before efficiency, right? You calculate your power loss, also based on the switching frequency that you've selected. Then you calculate your junction temperature. If your junction temperature satisfies your requirement, you can stop. I stopped here. I designed a buck converter. I can tell you, design a buck converter where the maximum junction temperature of the device is so and so. Okay, so how would you go about that? This is my buck converter. Right? We know that for the buck converter, what is the peak voltage of the device? The input. And the current is inductor current. The peak current will be the IP here. IP here means inductor current. Peak value of inductor current, right? So you know your VP and your IP. So you can select, so if you know your VP and IP, and you know your duty ratio, right? From your if you know your input and output, the output is equal to V input times duty ratio, right? So given your input voltage, given your output voltage, you can calculate duty ratio. If you calculate duty ratio and you know your V input and V output, then you can also calculate your average currents, right? I can calculate the average current flowing in this device, average current flowing in this device. This is D times IL. This is 1 minus D times IL. This is my average current, and this is IL, my average inductor current. Right? This is my average inductor current, and this is the peak value of inductor current. Okay? So I've selected what? From average currents in the devices, I know my switch average current, and I know my diode average current. Do we agree? I know these two from this exercise. I know the peak voltage across the devices is V input. So now I can select my MOSFET and diode. Right? You will find many choices. These many choices, how do you select? After that, you will select one based on the switching frequency that you will sort of assume at the beginning. So let's assume we selected switching frequency of 20 kilohertz. You're going to go and select devices that have rise times and fall times, rise times and fall times, that are, this 20 kilohertz is 1 over 20 kilohertz is what? 1 over 20 kilohertz? Half a millisecond? Is it?
5 something.
Yeah, it has a 5, sure. Is it 50 microseconds? I think it's 50 microseconds. 1 over 20,000 is what? Come on. Calculator. I don't know. I cannot seem to use the calculator. Yeah.
Oh, wait.
50 microseconds?
Yeah.
50 microseconds, right? So 50 microsecond is your period. If 50 microsecond is your period, then you want a device that will have rise times and fall times at least 10 times smaller than 50 microseconds. So let's say 20 times smaller than 50 times smaller. Let's say 50 times smaller than 20 microseconds. So you want a device with rise times around 1 microsecond, rise times and fall times. So select something like that. So T rise is approximately, select something like that. And then if you select something like that, a switch like that, then you can operate at 20 kilohertz with no problem, right? Because then you will rise and you will have enough time within the period to create a certain duty cycle that you want, right? And then what? So now you have your rise. You've selected your switch. One of the switches you've selected now. One sample switch you've selected. And then you have a restriction on, let's say, and then you can do that. Sorry, since now you've selected your switching frequency and you've selected a base switch, you want to go and calculate your L and C. How do you calculate your L and C? You look for the L, you look at your inductor voltage waveform, VL, and this is my delta lambda. L is equal to delta lambda over delta I spec. You may have a spec for ripple current. In this case, you may or may not, right? You may or may not. Your vendor here or the load here may require a spec for ripple current, or maybe not, right? They will typically have a spec for output voltage because this is what their load is connected to, right? I would like a load. The person providing you with this load, whatever that load is going to really worry about their ripple voltage. Maybe not worry about your inductor ripple current because this is internal to you. If you're talking about a boost converter, it may be a bit different because your battery is here. If this is a battery, and this is your inductor current, this is your inductor here, and this is your switch, and this is your capacitor output, and blah, blah, blah. Here, the battery vendor may put a restriction on inductor ripple current because batteries don't like to operate with ripple current, right? So battery vendor in a boost converter case, there may be a restriction on your input ripple current, and then there may be also a restriction on your output voltage because of your load, output ripple voltage because of your load, right? If you're a load, if you're worried about the load, you will typically be worried about the output voltage, right? If this inductor current is internal to the other guy's power converter, I typically don't care. But here, the inductor current is going to be drawn from my battery, assuming I don't put a filtering stage, right? If I don't put a filtering stage, the person here will be worried about my inductor ripple current. If this inductor ripple current has to be high, you as a designer can then put a capacitor here. Because if you put a capacitor here, all the inductor ripple current will go through the capacitor. And then you will end up only with the average current coming from the battery, right? But in this case, the battery vendor will tell you, I don't want somebody to draw out of my battery something with a current with a high ripple value. So this will be a constraint on your I spec, ripple current spec. Anyway, so you've selected an L and a C based on a switching frequency that you've chosen before, right? Then C is again, how do you select C? You draw the capacitor current, and then the area under the curve is delta Q. C is delta Q over delta V spec. So you've selected your L and C, given a specific switching frequency, right? And then what do? Then you need to calculate your power loss on the equation that we came up with, right? For the conduction turn on, turn off, and then the conduction power loss. And then you can calculate your efficiency, right? And then you can also calculate your junction temperature for the device. Let's say after all of this, you calculate and the junction temperature was too high, higher than what I said. I want to design a buck step down converter from 10 volts to 3 volts with I can give you an efficiency restriction. Let's say I give you an efficiency restriction. I want this to be 80% efficient. So you will stop here. Actually, before the junction temperature restriction, you will have stop here at the efficiency. And you will go back and calculate everything. You will see what was dropping your efficiency. Was the device dropping your efficiency? Or was we didn't calculate the losses in the L's and C's. Here we're just the devices. If you want to complicate things further, you can include the losses in the L's and C's. But for now, I'm not doing that, right? The only thing that will drop our efficiency is the device power loss, right? In this case. So if I tell you I want a certain efficiency value and you didn't meet it here, what do? You have to go back and in the power loss equation and see what can you change. The only thing that two things that you can change. You can change the device itself, which will change your rise and fall times, right? Because the P loss equation will have the T rise and T fall, which are depending on the switch that you've chosen. Or before changing the device itself, you may change the switching frequency, right? So you can go back and maybe change the switching frequency, increase it or decrease it, to figure out if you can meet the specs that I'm asking for or not. I can give you a range of efficiencies, right? I can tell you I want the converter to operate between this value of efficiency to that value of efficiency for a certain load range, for a certain average value of inductor current range, right? It's all the same equations, right? The equations are the same, but it's just you will have to go through the process maybe multiple times if I'm asking you to design something. Does everybody see this? Or so this will be on the exam, next exam. Is that fair?
Are you doing this on the exam?
It's fair, right? I think it's fair, right? So I told you, can you see it and you can understand it? And,
No, but
you
people
know.
usually do where
What? It's a good question to have on the exam, right?
One
Like
question, one answer on the exam instead of one question,
but
multiple.
I know you can have a design problem.
Okay.
It's just an idea. Go through it. Go through it. I would like you to go through this exercise, right? So design a buck converter and put some restrictions on junction temperature, or put some restriction on efficiency, or put some restriction, and then see how you can go through it. Okay? And show me the process. Show me the bonus point. How about that? Bonus point. 1% bonus.
Can you give us a thing?
Huh? 1% bonus. What? 1% overall. 1% overall. Here, design a converter. Design. Not now. It's
By when? When would you like it by?
on the exam. I think it's good. Yeah. Design a buck converter. Yeah. I will not tell you details then. Yeah. This design problem will be on the exam for 1% bonus in the full class. Okay. It will be design of either a buck or a boost or a buck boost converter, either of the three. Any one of the three, and it will include a restriction on either efficiency or junction temperature of the device. Bonus on the exam, or I will make it towards the bonus on the exam or bonus in the full class.
Full class.
Full class is better, right?
Yeah.
So it will be a bonus in the full class, maybe 2% bonus in the full class, but it will be during the exam.
So are you giving us the structure of the converter?
It's either one of the three, buck boost or a buck boost. I will not give you a new converter
Yeah,
architecture.
but you're going to give us the structure of it. I mean, the output is they're different. Like all of them.
But you have to, the circuit you have to memorize, the circuit you have to memorize. I mean, there's a good way to do it without having to.
I'm just double checking. We're only restricting efficiency. You might only ask us to restrict efficiency.
No, I don't. I said I will restrict something. I may restrict. May put an efficiency range.
Okay.
I may put a junction temperature range. I may restrict it to a minimum value of efficiency, minimum value of junction temperature. I may, not size, because then we'll get into inductor sizing and stuff like that. And then we will only consider the losses in the devices. We're not going to consider losses in the. And then for the diodes, we will only consider conduction loss in the diode. So the diode conduction loss will be what? Just the forward voltage times the current, basically. Okay. Average value of that, of course. So, is it clear? Is this design problem clear?
No, if you want to give us
More hints? I think it's.
an example,
So
Oh, we don't want to.
is in the homework. Is something like this in the homework?
No, I don't think so.
That's okay.
No. Yes, sir.
tell me if I'm getting anything wrong here. So first we identify the output voltage with the input, we have the input voltage.
Of course, because you will typically be given a certain output and a certain input voltage, right? Because your load will require a certain output voltage. Any load will, and then you have a restriction on your input voltage. It can be a single value, or I can tell you that the input voltage is a battery whose range, when the battery is charged, it's 11 volts. When it's discharged, it's 10 volts, for example, because that may change the efficiency, right? That may change your efficiency. I can change any variable. But I'm trying to say that the equations are the same, but I can change any variable. So let's say it's given a certain V input and certain V output, and I tell you it's a buck converter, right? And I tell you, let's say I put a restriction on. Let's say I tell you I want this converter to be I want a power output, let's say 5 watts. And I want this converter to operate with an efficiency of, let's say, 90% minimum. Right? So this is, let's say this is 10 volt input and 5 volt output. So I know my output voltage, right? And I know my output power, right? So I can calculate the output current. This is my output current. Then I know my efficiency, right? I know my input voltage, this is 10 volts. I know my input voltage, right? How do I calculate my input current? I know that I have an efficiency of 90%, right? So, which means that 10% is lost here. But I need 5 watts at the output, right? So what's the input power? Efficiency is P output over P input. P output is 5 watts. And I should be able to calculate P input for a certain value of efficiency, right? So if I have my input power, that input power is V input times I input. So I can calculate my input current from the battery. This is my input current from the battery in this case. Then, the idea is now I would like to select my devices. Or I may, for example, give you a datasheet for a MOSFET and datasheet for a diode, right? And then if I give you a datasheet, then I'm fixing the devices, right? If I give you a datasheet values, because then you want to select You know your input current from the and your battery voltage. Then you want to select your diode and MOSFET. You need your peak value of voltage. What is it for this buck converter?
So, inductor.
It's 10
Oh,
volts.
sorry.
10 volts. V input. It's a buck converter, so it's 10 volts. Right? So it's select your switch will have to have a peak voltage of 10 volts. How about average current? The average current. How do I calculate average current? Again, let's look at how do we look at this average current. Let's see the average current. IN is your average input current. Yes, exactly. Is your average battery input current is your average current. That's the current that's flowing through the MOSFET when the device is on. How about when the device is off? The current is flowing through the MOSFET, right? So your average input current, yes, your average input current in this case would be IN. I agree, that's the average input current. But this average input current would be pulsed in nature, right? You may have to put a capacitor here in that case. But let's say without the capacitor. This is your average input current. If your average input current, IN, is equal to, let's say 1 amp, for example. It's not 1 amp. What does this current actually look like? It's actually pulses, right? So your current here, when the device is on, you will have the pulse. When the device is off, and this will have an average value, D times I peak. D times I peak, which is equal to IN, right? Because we said that this is your average input current. This is your average power. This is your average input current. So now I know what? I know my peak current. Now I know the peak current flowing through my inductor. Because what is this? If this is your switch current, what does your diode current look like? Same peak current, but for the 1 minus D. Same peak current, but for the 1 minus D time period. Right? This is the same peak current as the inductor. Because it's the same inductor current that's going to flow through this inductor current. Part of it will come from my device, and part will come from my diode. The part that will come from your device is equal to D times IP, right? And here it's 1 minus D times IP, right? Or D times IL, or again, I'm assuming small ripple current, right? If I assume small ripple, if I'm talking about average values of current, then it's IP would be my average value of inductor current, and this is D times IP, and this is 1 minus D times IP. Okay? Yes? So now I found my average values of current. I found my average value of current for the device, MOSFET, and the diode. Now, and I have my peak voltage for the devices. For the devices, I can go select the device. Let's say I give you a data sheet with the devices. Right? Then I'm dictating what? I'm dictating a specific device, so I'm dictating rises and fall times. Right? So the only thing you can play with in that case is what? Switching frequency. Right? You cannot play with anything else. Right? Okay? But if I make it an open book exam, I don't know, I'm just if I make it an open book exam and I ask you to select a device from the IR website, then it can be a range of devices that you can select. You can select a range of devices, and it can be freer for me. I can tell you, okay, I want efficiency range to be a certain value, I want power loss to be a certain value, or I want temperature junction temperature to be a certain value, regardless. But let's say I give you specific devices to use, right? Then after you've selected your devices, based on the peak voltage and average currents, which we've calculated here, given there's an efficiency, right? We've now given that there's an efficiency. Then what do? Then you draw the current, then you have select, and the fact that you've drawn this, it means that you've selected a switching frequency. Right? Since you're drawing this, it means that there's an on time and there's an off time. Right? I'm drawing this, there's an on time and off time. There's a duty cycle that you've chosen that's dictating the ratio of on to off. Right? But if you want to put a T here to there, to this thing, to this waveform, that means you've selected a switching frequency. Right? So you've selected a switching period or selection of switching frequency. Then you can go and calculate your inductor size, capacitor size, and then you will calculate your efficiency. It should be what? It should be 90%, right? Because you've already assumed it's 90%, and that's how you calculated your inductor current, your input current, right? From the fact that there is a 90% efficiency, then you calculated the average value of input current, right? This average value of input current came from the efficiency, right? Okay, so the efficiency here should be 90%. But then, let's say I asked you to make sure that the junction temperature of the device is greater than, or sorry, less than or equal to 90 degrees C. Then what do? The only thing you can do if I give you the devices to use is to change the switching frequency, right? So if I tell you I would like the junction temperature to be within a certain range, then I've helped you specify the range of switching frequencies. What is the corresponding range of switching frequency? To make sure that the junction, this is easy. If I give you the data sheet and specify the device, then all I can do, for example, is to ask for a range of switching frequencies that will make the junction temperature vary between a certain value and another value. Do we agree? Yes, ma'am.
You give us the ambient temperature, right?
Yeah, I'll give you the ambient temperature, of course. But if you have more than one device to choose from, another question can be, okay, what is the range of switching frequency if you choose this device? What is the range of switching frequency if you choose this device? If you want junction temperature to be a certain value, right? So you can compare devices that way, right? It's a design problem. It's a design. I mean, I don't think it's difficult. I just, it will force you to go through the process here, right? So try to go through the process with the devices that I have on the website, and select a suitable range of switching frequencies to maintain the junction temperature between two certain values that you select. Okay? So go through that, and if you have problems, come to my office. Okay? I think we spent a lot of time on this. And then just a little detail on the junction, this thermal resistance, right? Because in the data sheet, sometimes you will see, they will give you thermal resistance, okay? This is, again, this depends on many things. Here you have a device that has a junction, and then there's a case. So between the junction and the case, there's a thermal resistance. Sometimes in the data sheet they will not give you, sometimes they give you R thermal for this device in air, which includes the junction to case, and then the case to the outside environment. Okay, so, or sometimes they give you RJC and then R case to ambient. Right, so sometimes they give you both, or sometimes they give you one of them. Okay, so just something to consider. If you're going to put a heatsink, right? So let me make this look like an electrical circuit. This is power loss. If this is an analogy to an electrical circuit, this will be power loss, and this will be your ambient temperature, T ambient. So this is my ambient point. This is my ambient temperature. Let's say this is 25 degrees C. Right? If this power loss is the current flowing in here, then this is what? This voltage drop will give me my case temperature, right? And this voltage drop will give me my junction temperature, right? Or if both of these can be my thermal resistance, R theta, if I just call it R theta, then both of these, I can represent that circuit that we did before, or the equation that I wrote, as the following. This is T ambient, and this is R theta, and this is T junction, right? Isn't this a representation of T junction is equal to T ambient plus R theta times power loss, right? Because this voltage drop here is R theta times power loss. And then if I add it to the ambient temperature, it will yield my junction temperature. That's the analogy here. So sometimes you are not given R theta as R theta because sometimes they know that you will heat sink this device. So if you're going to heat sink this device, what will that change? Is it going to change the junction to case temperature?
Case to
Sorry, the junction to case thermal resistance? No, it will probably change the case to ambient thermal resistance, right? Because this case sometimes can be hanging in air or sometimes can be on a heatsink, right? If it's on a heatsink, then you will change this. How am I going to change this? I'm putting something sort of in parallel. So the junction to case is typically going to be a small value. Junction to case is a very small value. Junction to case, here around it to be a very small value. The heat will move easily from the junction to the case. Typically a very small value. And then the case to ambient is what is typically going to be a big value. Let's say 100 degrees C per watt, for example. Then let's say this is 5 degrees C per watt, for example, right? Then what do you want to do? You would like to put a heatsink in parallel to this resistor to decrease it, right? So this heatsink, when you go select heatsink, it's also based on thermal resistance of the heatsink. So it's also degrees C per watt, right? It has to make sense because this is a thermal resistance in parallel with another thermal resistance that has units in degrees C per watt. So let's say the heatsink will then have 50 degrees C per watt thermal resistance, right? Then what is the effective new structure that I have? I have a resistance here, RJC, and then this one here is a parallel combination of 100 times 50 over 150, which is what? $500 divided by 15 is how much? Come on. What's 500 divided by 15? It's more than 50 and it's less than 100. Sure, great. Anyway, it's more than 50 and less than 100, right? So what did we do? We were able to decrease the temperature rise between ambient and case, and since this didn't change, then my junction temperature has also decreased. So how much I decrease or how much I maintain my temperature will depend on this heat sink I add in parallel, right? This is one-dimensional heat transfer, right? Of course, this is very rough back of the envelope type heat transfer calculation. Okay. So another question can be, what is the required thermal resistance of a heat sink to maintain your temperature of the device below certain value, right? And in most device data sheets, you will get RJC and RCA. Most of them, you will get both of them. Okay? Yes, ma'am.
So can you just repeat why the RJC, the temperature is lower if you add the heatsink in parallel?
No, JC does not change.
It doesn't.
No, JC does not change. What changes is the case to ambient. The junction to case. The silicon is inside the case. I mean, whether I put a heatsink or not does not change the effect, the ability of the heat to go from the junction to the case. That ability is defined by RJC. That does not change. But the ability of the heat to go out from the case to the ambient will change if I put a heatsink, or I don't put a heatsink, right? It will change. So that's why it's represented as a parallel resistance to the RCA, case to ambient thermal resistance. Okay. Okay, that being said, wow. That being said, we've considered the voltage drop across the switch, for example. How does voltage, but all the analysis we did before was for ideal conditions, like when we calculate the voltage ratio, calculate the inductance ratio, value of inductance, capacitor, etc., etc. So how does really considering the voltage drop across the switch or voltage drop across a diode, affect the output voltage for the buck converter and for the boost converter. So we can go quickly through the analysis. For the buck converter, when the switch is closed, inductor voltage is equal to what? When the switch is closed, inductor voltage is equal to, switch is closed, diode is open, inductor voltage is equal to source voltage on one side minus V output, right? Source voltage minus V output. But when the switch is closed and I consider the voltage drop across the switch, I have to subtract that as well from the equation. So it's Vs minus V output minus Vq, the voltage drop across the switch Q. How about when the switch is open? When the switch is open, the diode is closed. When the diode is closed, I have 0 on one side and then V output on one side. So it's 0 minus V output is the voltage, but it's not 0 minus V output. There's a diode as well. There's a diode forward drop that I have to consider. So it's minus V output minus Vd that I have to consider. Right? So when the switch is open and when the switch is closed, we looked at the inductor voltage. Then, remember, average voltage across the inductor has to be 0, and that's called volt-second balance. So average inductor voltage is 0 over the switching period. What does this mean? VL, average value, is equal to 0. Where? Over the switching period. So what's happening? When the switch is on, this is for duration D. When the switch is off, it's for duration 1 minus D. So the average voltage across the device, across the inductor when the switch is on, plus when the switch is off, that is equal to 0. I get, if I solve this equation for V output, I will get Vs is equal to, V output is equal to this equation. If I cancel these terms, if I cancel this term and this term, I get what? V output is equal to Vs times D, which is my voltage transfer ratio for the buck converter, right? So for a buck converter, what is the voltage drop across the switch doing to my output? It's decreasing it further, right? So, which means that for a buck converter, there will be, theoretically, we should be able to operate between 0 volts and input voltage, right? So practically, we can go down to 0 volts, but we cannot really get input voltage. We will have to have a voltage drop across the devices, right? So the effect on the buck converter is not drastic, right? Because we want to reduce the voltage anyway, but there's a part that is uncontrolled, right? So there's a little bit of a drop initially that is uncontrolled. So if you're trying to go from 0.9 to 0.89 volts in a buck converter, it may be difficult to achieve that. You will really have to select the proper devices in that case, because your switching losses the voltage drop across switch will affect the output. But if you're trying to go from 10 volt to 5 volt, it's okay. The switch voltage drop is only helping me, right? I'm trying to reduce from 10 to 5. But if I'm trying to reduce from 10 to 9.99, then I seriously have to consider the voltage drop across the switch, because it is actually affecting my output voltage, right? So basically, in a buck converter, there's no huge effect on the output voltage due to the switch voltage drops. Yes, sir.
Do we use a buck converter for a less precise voltage drop?
Typically, no. Typically, if you want to be very, very precise, then you would use a linear regulator. And in a linear regulator, remember, in that case, will make a lot of sense, because there's no huge voltage drop across the device that is called doing the linear regulation, right? The MOSFET or the transistor that's doing linear. So I would use, when it's that close, I would use a linear regulator. And typically in power electronics, actually what we do, typically you have a power supply, switching power supply, followed by a linear regulator if you want to feed a processor type load. Because processor loads require nice clean voltages with low ripple. So you typically, it's called post-secondary post-regulator. It's a post-secondary regulator. Okay, discontinuous current mode. Remember, we talked about, for the buck converter, we always talked about the fact that inductor current is continuous. How about if inductor current is discontinuous? Does it change the requirement for average inductor voltage equals 0? Does this change ever? Or average capacitor current equals 0? It cannot change. This is consistent, right? So even when we operate with discontinuous buck converter current, what will happen? What we will see is, again, this is my buck converter. when does the average inductor current do this? When do I go from continuous mode to discontinuous mode? When I do what?
When you have the larger load.
Yeah, when the R is larger. When R is larger, meaning the average value of inductor current keeps going lower and lower and lower and lower for a specific delta ripple. Right? Your ripple current, let's say your ripple current is 5 amps peak to peak. Right? If your ripple current is 5 amp peak to peak, then this is delta I equals 5 amp. If this is your ripple current, right? What is the average value here? 2.5 amps, right? If your average value of current is lower than half your ripple current, right? If your average value of current is lower than half your ripple current, then you have gone into discontinuous mode. Remember, ripple current is always, delta I going up is equal to delta I going down. And the average value is equal to half the ripple current plus the average, assuming there's no shift here, assuming that you're at your critical value of inductance, then your average value is equal to half your ripple current, right? So if your average value reduces below half your ripple current, you go into discontinuous mode. But in discontinuous mode, the average inductor voltage has to equal 0 as well. So we can use that equation to figure out what the average, remember, what we want to do is figure out what our duty ratio will be if I go into discontinuous mode. For the buck converter, V output is equal to D times V input. Where? In continuous mode. When I have continuous inductor current. Okay, what does V output equal in discontinuous mode? Is it also D times V input? No. It's something else. Right? Our assumption was D times V input was continuous inductor current. So what is it equal to when I have discontinuous inductor current? So what do? We have to use volt-second balance, meaning what? I have to look at the voltage across the inductor when the switch is on. Again, this is my buck converter. This is my inductor. What is the voltage across the inductor when the switch is on? It's V in minus V out, right? V in minus V out. When the switch is on, meaning for period of dt, right? The switch is on for period D. Now, the switch is off and has current for a period of D1 times T. It's no longer 1 minus D, right? The difference between the continuous and discontinuous current is that in continuous current, the switch is on for D, and then it's off for 1 minus D, right? 1 minus D is all of this period. But during all of this period, I don't have current. I only have current for this small period of it. So this small period of time, D1 times T, is when I have to look at inductor voltage when the switch is off. So when the switch is off, the output voltage across the inductor is what? Switch is off, diode is on. Voltage across the inductor is equal to V output. It's V output times D1 times T, not V output times 1 minus D. That is the difference between continuous and discontinuous. After I've done that, I can calculate, simplify it a little bit. Do I have now the required duty ratio that I want? No, because I don't know what D1 is. I know D. D is the period the on time of the device. So what the proof that they go through the textbook, they will calculate D1 in terms of circuit parameters. I'm not asking you to know the proof. So basically, here I have an equation relating what? Input voltage, output voltage, and duty ratio. But it has something I don't like. Which is D1. So in the textbook, and I'm not asking you to know the proof, in the textbook they find a way to relate D1 to everything else that we know. Okay, to D, R, and L of the power converter. And then what can I do? I take this new D1 and substitute in this equation. Right? So if I do that, I can remove D1 and write V output in terms of things that I know, right? I can write V output in terms of V input, duty ratios, and R and L and switching frequency. Right? That's the process. So I'm not asking you to know this, it's an equation, this is something right? And this is just waveform drawings, right? Because when the switch is on, this is V input minus V output, switch is off, it is V output for a shorter period of time equal to D1. Still have a few minutes. So any questions on this? Here, what this slide says, I'm just, remember the discussion I had before about linear versus nonlinear, continuous versus discontinuous mode of operation. The output voltage equation will change, right? When a buck converter is operating in continuous mode, V output is equal to V input times D. So this is V output. If I increase D, I will increase V output, right? That is the case for continuous mode. How about discontinuous mode? Discontinuous mode is governed by this equation. This equation, what does it look like? It looks like this curve, right? So this curve is very different than this curve. So in continuous mode versus discontinuous mode, you don't control the transfer functions of the converters. The converter is different, right? So, and I will come to that later in the chapter. Yes, ma'am.
So
Go ahead.
the output is higher in discontinuous mode, like generally, in the nonlinear.
For the buck converter, yes. For the buck converter, for a smaller duty cycle, I was able to get higher voltage. Okay? Versus the continuous mode. Yes?
How do we know it's continuous or not?
That's the I minimum that we remember. That's the I minimum that we always been calculating all the critical value of inductance. So we were going back here. If you go back to here,
Yes, and continuous first, and then we calculate the.
yeah, we were calculating I minimum, and we were equating this to 0, and we were calculating the minimum value of inductance that we can use, right? So that's the relationship here. Good question. I mean, now I think if you're thinking of that, means that you're closing the loop now. You're closing the loop between what we were saying before and now. So, and then the same thing with the boost converter. Okay, there is some effect on the boost converter if we include losses, and we talked a little bit about that before. But the process is this. The ideology, the idea is very similar. The idea is we have to find a relationship based on the volt-second balance of the inductor. So we look at the switch inductor voltage when the switch is on, and then we look at the inductor voltage when the switch is off, and then average value of inductor voltage is always 0, right? So when the switch is on, inductor voltage is equal to input voltage, Vs, right? So it's Vs for dt, right? That's Vs dt. That is the average voltage across the inductor when the switch is on. How about when the switch is off? Again, we have the same distorted D1 that we don't like to see, right? But this is where the current is flowing, so it's Vs minus V output. That's the voltage across the inductor when the switch is off. When the switch is off, I have Vs and V output on the other side. So Vs minus V output times D1 of t times D1 times t is equal to 0. That's the average voltage across the inductor for the whole period. It's equal to 0. So here I do the same thing. If I solve for V output, I will get something in terms of D1, correct? If I solve this equation for V output, I will get an equation in terms of my input voltage, which I know, and then the output voltage which I require, the duty ratio that I control the switch to, but also something I don't like because I don't know, which is D1, right? This value of D1 is not 1 minus D. This value of D1 is a value that will depend on the LR time constant of the circuit, right? So same thing, in the textbook, they go through a proof and they find a value for D1 in terms of input voltage, output voltage, circuit components. You take that and substitute into this equation. Okay, the logic is the same, right? The logic is very similar. So that's discontinuous mode for the boost converter. What is that doing? Sorry, that's the discontinuous mode. These are the corresponding waveforms for discontinuous mode. Again, average inductor voltage has to equal 0, like we've discussed before. What is that doing to the boost converter? Remember, what did the boost converter input to output voltage characteristic look like? It looked like this, actually, right? So here, what in discontinuous mode, what it's doing is it's making this part look straight, like a straight line, versus, right? It's not affecting the control too much, but this is a straight line versus before it was what? A 1 minus D, right? For the boost converter, what was the output voltage?
Over 1, VS over 1 minus C.
Yeah. This was my output voltage. Output voltage was like this. It was not a straight line, right? There was no straight line section here. It was all this parabola that's defined by Vs over 1 minus D, right? It was Vs over 1 minus D. It's all a parabolic equation. But now in discontinuous mode, there is a bit of a straight line. So you will have to consider that in your control design. So that's discontinuous mode for the boost converter. Then they do some simulations. Then this is something I will do this next time. So this is where, so now we've looked at the buck converter, boost converter, and the buck boost converter. Continuous mode, right? And we know how to play with that very well. And then discontinuous mode, we sort of see that the only difference there is I have a D1 that I have to recalculate, and it will affect my control a little bit, yeah. The final topic I would like to discuss, and I will do that next time, is, okay, now this circuit, I would like to control. I talked about continuous mode and discontinuous mode, fine. And I said that we need to control the power supply. How do you control the power supply? You have to find a transfer function for the power supply. Right? For the buck converter, how do you control it? You create a duty cycle, that's fine. But what if, let's say your input voltage is 10, your output voltage is 5. So you will select a duty cycle. Okay? What if I remove the load? What happens? Or if I change the value of the load, what happens? If I remove the load or decrease the load suddenly, you will. If you think of the car, If you're driving with your car, and all of a sudden you find a mountain, what happens to the car's speed? Even though your foot is in the same place on the accelerator, it will slow down. Why? Because of the transient response of the circuit, right? So next time, which means that we have to take these transient response into consideration. So in 420, you're studying that. So how does this come into play in our circuits? That's what we will. I will briefly go over that next time. Yes.
So do we have class on Monday? Or Wednesday? Which days that we don't have class?
We don't have class Monday.
Over the